Okay, let's go ahead and go through MapReduce, and what I'm hoping to go through today is to go through, it sounds stupid, but just the hello world example. And then parts of it is also going through the class hierarchy, but the biggest piece is to actually begin to understand exactly what it is that MapReduce is trying to do, and the class of problems for which it makes sense, and then probably some for which it doesn't. And then what I'm going to do is we're going to have a simple assignment, which will be basically getting the second version of the hello world example to function correctly in your virtual machine. And that's going to be basically the setup for another assignment. So that should only take a little bit of time. The second assignment, I'm still trying to figure out exactly what the piece is. There's one that I have from last time, which involves gleaning information from a patent database. So it's patent data, and then about which states, so you could use it to ask questions about what state have what patents, and or how many patents, and so on. And but that requires us to be able to do data joins in Hadoop, and I have to figure out how to do it in version 2.5 versus 1. Whatever that I had done it in the last time for that. So let's just go through and sort of summarize some pieces again of what we had done. So basically the way that the map and reduce phase works is that we have a pile of input data. We're going to see that gets broken up into what are called splits of files. The individual splits are then distributed to a given node where a mapper will run. The levels of, so you shouldn't think of this as being a one-to-one mapping necessarily. So in other words, I might have 2 nodes of data or 2 nodes of processing power, but I might have thousands of mappers, which are going to then go over a chunk of data. And the reason for that is simply one of scheduling efficacy. So in other words, there may be one chunk that takes a lot of time compared to another chunk. If I just took my data and I divided it into 2 pieces and said, you run this and you run that, then I might have load imbalance such that one's going to take a lot longer to finish than the other. Later on, we're going to go through, I'll post a paper, but more or less the summary of the results is something, it's like big data and the long tail or something like this. There are certain jobs or certain processes and activities that you have where 99.9% of them will finish reasonably short, but then there's that really long one. And in this kind of a workload, the whole thing doesn't finish until that long one finishes. So a file is broken up into lots of little pieces. The individual little pieces are then scheduled. And then you can do adaptive scheduling across that. So then we go through a map phase, and in the map phase, we're going to basically apply a function to the fields of that file. We'll go through again what that is. And then we're going to have possibly a combining phase down here. We'll go through what that is a little bit today. And then the data is shuffled, so the shuffling makes it such that all the keys for a given type of data is at one node, and it can then be reduced at that point. And then this is stored in the data set for that particular node for that. So conceptually, the diagram would look like this. We have some input files. And in the mapping phase, we're going to apply something to these different shapes. But in the sorting phase, for example, all the elliptical shapes are on one node, representing one kind of key value. All the pentagonal nodes are in another hexagonal, I guess, and so forth. So the key values, it's not that any one reducer has only one kind of key value. So for example, this one on the right-hand side here has both the stars and squares in it. The mapping of who gets what key value you can control, sort of. But the big piece is that all of the ellipses will be here, right? And so we'll go through a couple of examples of where that might make some sense to do. So the map function, it's a little bit more complicated than that simple Python example that we looked at. So basically, map is going to take key value pairs, and it is going to output a collection of alternate key value pairs. So map is invoked for a given key and value, and the key might be, for example, the line number of a file, and the value might be the contents of that line. Or if it was tab-separated data, it might be the first value is the key and the second data is the rest of that data. If it comes from a database, it might be something else. But it's all key-value pairs. All right? And we're going to see that in a lot of different data systems that you use in big data. Key-value is a very common representation for things. So there's the Cassandra file system or distributed database is a key-value pair system. There's a whole bunch of other level DB. There's a bunch of different things where it's all key value. And from that, you can then build other things for that. So the output collector here, the reason that this isn't just that it's returning a key and a value, is that you may be returning multiple output values for a given input value. We'll go through an example that does exactly that. And then there's a reporter, and the reporter has counters and other data structures associated with it so that you can see the process of what's going on. Because debugging this is fairly difficult to do. So here's an example from that WordCount tutorial of a mapping function. And this is why Java is awful for this, okay? So what we have here is, so this is a tokenizer mapper. It extends the mapper class. It's with an object and text. So the key is an object, I guess, because there's nothing there. It's taking a text as input, and it's going to then produce text output in an int writable. So in other words, what that means is it's going to be taking a key value where the key I don't care about. The value is a text value, and it's going to be outputting text paired with an integer value for that. So then for efficiency here, they create a single int writable. We'll see what the writable classes are. It's part of the Hadoop structure of things that get outputted. And you can define your own versions of this, but so there's an int writable, a long writable, things along those lines. So here what they're doing is they're just basically defining a constant 1. And because this is Java, they don't want to make a bazillion different objects, because then they'll all have to get garbage collected and it'll take more time. So they're creating a single instance of the number 1, and then they create a single instance of the word text. And they're going to then update that instance repeatedly for that. So this is then the map function that's actually called. So it's been given a key and a value. It doesn't care what the key is because it never actually uses it. It has a context. Oh, maybe so this is a context now. Sorry, this is the older signature from version 1 of things. So the context has much more information about what node it's running on and a whole bunch of other stuff that is handed by the job scheduler for it. So all this is then doing is going through and it's taking the value, saying extract it as a string because it's a text, chop it up, so it creates a new string tokenizer, which is some Java class that just chops it up based upon spaces in this case. It now has an iterator where it can then go through the individual tokens, and it's going to set the output of this word value to be whatever the next token is, and then it's going to write word and 1. All right, so it's taking a line, it's chopping it up into space-separated things, and it's writing those all out with the number 1 attached to them. So the line dog dog would emit 2 output records in this particular case because we would have dog in 1 and dog in 1. So this is like about as dumb as you could be. So it's not looking at anything within the same line or anything along these lines for that. So if what we had was 2 input files, like where the first one was hello world by world, misspelled, then what we would have is a series of output records that would look like hello 1, world 1, by 1, world 1. It's just that line chopped up into words spit out. If there was another input file that said maybe on another node, so it's been split and the mapping is being done on 2 different nodes, we might have hello Hadoop, goodbye Hadoop would be goodbye Hadoop, Hadoop, hello at that point. Right? And that's just exactly what that's all that the output does. Now, there's a bunch of mappers that are built in. And so, like, you could look at this mapper and go like, geez, why doesn't this do at least a simple reduction? Because I'm writing word count. Why doesn't it have like a local dictionary and look for the word hello twice or things along these lines? We're going to see that basically the goal is to try and have the map and reduction phases be reusable for different purposes. And if I was trying to do something where I was reducing the unique number of word counts on this, then I wouldn't be able to necessarily use this mapper for other things. I could use it for word count, but I couldn't use it for something else. And you could certainly write that if you wanted to. We'll see there's another way to basically get the same effect. And so there are a lot of design decisions where you kind of look at this and go like, what on earth is this person doing? Because this is so inefficient. How can this possibly work? But the thing to recognize here is that the inefficiency is sort of secondary, because the goal is to be able to get you to do something that can run on 1,000 nodes as well as 10, without you having to know that you're running on 1,000 nodes. And it's that efficiency, that's where you're going to get the 10x efficiency. So if there was a 30% efficiency here of having, an interior dictionary or something along these lines, maybe that's not where the big savings is. And we'll see other ways to do that. So this would be the output of that phase. So there's a bunch of mappers. And so, for example, identity mapper just maps the input to the output. We'll see later on where we might want some of those. And that's because we always have to have, so we might not want a mapping so much as a shuffle. So in other words, we don't want to change our input data. We want to group it so that in the reduction phase, it's all on the same node. And that's the critical thing, right? And the shuffle is the time-consuming part. So there might be an inverse mapper. So that's going to just map key values to values keys. A regex mapper. So that's going to then generate from a regex. You can have patterns that are there. For that, a token count mapper. So this is basically what word count implements. There's a whole bunch of mappers, and if we look at, let's see, where's the, in the tutorial web pages, there's a class index, and I'll be posting this, that goes through all of the different classes, and you kind of look at this and your eyes glaze over, because it's like typical Java, just sea of garbage. That it's very difficult to understand what the structure of it all is. And so the browser view over here winds up being essential. And we'll take a look at a couple of the things that wind up being important for us to do. So there's a bunch of mappers that are already implemented, and any organization would probably have their own mappers for specific classes of data types that they would be dealing with. For that. So then we have the reducer. So the reducer is taking a key of some type and then an iterator of those keys. So, and it's then going to have another output collector, and so there would be a separate key value pair at that point. And I think that this reporter is actually supposed to be the context thing again, because I forgot about fixing that. So the reducer goes through these different stages. First there's a shuffle stage. So the shuffle stage is everybody's data from all the mapper nodes that has the same key is going to go to the same reducer. So, and this is going to the same reducer node. So I might have different mapper and reducer nodes in my physical system.
When you're doing the intermediate key value pairs, do they get streamed out to the reducer nodes, or do you have to finish an entire chunk?
I think you have to finish an entire chunk. I was trying to figure out in the implementation exactly how that works, but the issue is that then next there's a sort phase. So before the reducer actually begins to work, what the reducer is being given is a key and then all of the values associated with that key. Does that make sense?
Yeah. So if you go over your memory, then you're going to have to start writing it to disk then?
Yes, and in fact, that is the default set of operations, is that it's very disk intensive at that point. But if you think back to sort of where this came from, there was actually a really cool, let's see if I can find the photo. back in the late 90s, I took a leave of absence and I worked at a place, the DEC Western Research Lab, and a bunch of the people, so Luis Barroso is one of the people that I worked with, and he's now at Google. He was an early employee at Google. He works on data center design. We'll be going through some of the stuff that he has. He was at that time working on high-performance microprocessors. This was the 1,000th rack that Google deployed. So again, remember, Hadoop is a cheapo version of Google's MapReduce framework, which was not written in Java. I'll tell you that. So it was a C++ runtime structure for that. And it's, the engineering is a little bit different for it, but more or less the functionality is about the same. So this was the 1,000th rack that Google deployed. It doesn't mean that at the time that they had this, they had 1,000 racks. Because some of them had been retired by the time they got here. But so the design choices that are made in Hadoop are made at a particular point in time and about how things function. So each of these servers here is, so it's it would have been at that time a Pentium P4, something along these lines, probably 2 disk drives, 3 disk drives, something along these lines. They built their own, instead of wrapping tin around it and having their own airflow and everything else, they basically just built their own motherboards and racks to design to accommodate their own standard server design. The model of this was that the individual servers are prone to failure, and so they wanted to be able to just, like, if there is a failure of a node in a rack like this, they just pull it out and swap in a new one, and then it gets remotely re-imaged at that point. So one of the things Hadoop is doing is it's also designed to be able to manage the failures, just like MapReduce did. So in other words, if a mapper is running or a reducer is running and it dies, it's going to restart and it's invisible to you at that point. All right, so that's all happening under the hood as well. So the other thing is, each of these nodes basically had like gigabit Ethernet, and you can pump, a little bit over 100 megabytes per second on gigabit Ethernet. Your disk drives that are on here, you could get 100 to 300 megabytes per second off of each drive. So if I have 2 or 3 drives, maybe I can get 500 megabytes of local I/O and about 100 to 150 megabytes between nodes I/O. Right? So at that point, the sucking data off of a wire and spooling it to a disk file is not that big of a deal, right? Because what I'm really limited by is the bandwidth of the network at that point. Does that make sense? So it seems like a funky design decision, but it's sort of really focused upon what was their deployment architecture. If I start having 10 gig networks here between the nodes, and so these networks, will go through basically what a typical organization would be, but you'd have a rack and you might have, each node would have typically a gigabit network up to like a 48 port top of rack switch, and then you would have, your top of rack would have either 10 gigabit or multiple 10 gigabits bonded that goes to your row switch, and then you would have a set of data center switches after that. And so you have limited bandwidth between nodes on that. And much of the optimization was to take advantage of that, or to try and work around having the limited bandwidth between the nodes. Some of this would obviously be different today. Yeah.
So, well, given what we saw about how the reducing function works, and given this like bandwidth between nodes problem, does that mean that MapReduce for problem spaces that are not embarrassingly parallel or like easily parallelizable, do you end up with like weird issues where if like one node is getting like you didn't know that after the map phase one of your nodes was going to get like have a key value that was huge?
Right.
Yeah. Then does that end up slowing down like the whole process, or is there?
Yeah. Because it's basically map, reduce. You're going to do that pattern multiple times for it. WordCount's just going to do it through one phase for that. But yes, that is exactly the problem. And it's also, that simple map reduce pattern and repeating that multiple times is also where, like Apache has this yarn, yet another runtime, I don't know what the N stands for, but a runtime system that is basically managing the parallelism and scheduling of what's running and where. And it allows you to do more sophisticated scheduling tasks. That's the same thing that when we look at the Spark system, what we'll see is that there's an evolution from the advent of 64-bit architectures allows you to cram a lot more RAM on a given node. And so then you can begin to do a lot of processing at RAM speed instead of at disk speed. And so there's a desire for certain query systems, like I want to ask a question, get a response back quickly, where you're going to now have an in-memory database as opposed to an on-disk database. And now the model has to change a little bit, because you don't want to be streaming in vast amounts of data and doing the same kinds of things on the assumption that it goes to disk. And that's where we're going to, when we look at Spark, that's an example of doing that more recent in-memory model. But you can still persist things to disk for that. And we'll see that, so today, I mean, it is still the case that, so in a lot of stuff in the mid-90s, there was this whole, and it's probably important to understand from a contextual perspective, but so there was a whole series of, in the mid-90s, of mini supercomputer companies and supercomputer companies. We used to have actually one of every dead and dying supercomputer in the world here. And so these were basically launched, the market started in sort of like the late 80s and early 90s. And the goal was to be able to have people write like big honkin' Fortran programs to do, you know, fluid dynamics or whatever at that point. And the reality of it was much of the development of that equipment was then subsidized by the Department of Defense, because a big thing that they were actually doing was bomb physics simulations. So the biggest innovators in supercomputer and the high-performance supercomputers has historically been Lawrence Livermore National Labs, Los Alamos National Labs, Oak Ridge National Labs, Argonne National Labs. Only Argonne doesn't blow stuff up. Right? Argon just tries to make protons go fast or something like that. But it's still a high-energy physics kind of thing. Right? The other ones blow stuff up. And so in the mid to early 90s, then after the fall of the Soviet Union at that time, there was a test ban treaty, weapons ban, couldn't blow stuff up anymore, so on and so forth. So then you had to start doing simulation of bombs blowing up. And so there was a whole effort called the Stockpile Stewardship Initiative, a bunch of other things, which is we're going to make big honking computers to simulate bombs blowing up. So those big honking computers had lots of, they were much more sophisticated than this baby here, all right? Through my own evolution of watching all of these computers arrive and then people learn how to make them work, we used to have like a machine made by a company called Kendall Square, shared memory machine, 512 CPUs in it. Getting it to work well for your code was relatively complex. So even the science people, once the defense budget kind of collapsed again on this, even the science people started going like, well, let's just take regular old computers and stick them together with networks as opposed to making special purpose computers, if that makes sense. So that became then a whole series of specialized networks, but typically commodity CPUs. The business people, sort of in mid-1990s, were buying stuff like big honking computers. So Teradata is an example of a company that makes big honking database processors at the time. And apparently it doesn't help with their websites. And so they made at the time big systems that could collect, for example, all the inventory data from Walmart. I once drank beers with a guy who sold Teradata to Walmart, and he said before that they actually used index cards in wherever they are, Alabama. And they had like people. So like there was the coat person who had their view of coats across the entire United States in index cards on inventory for different Walmarts. Like that. And so the goal was to then be able to get more data. So Teradata was one of them. There was other companies, so eBay, which you probably know about. So eBay in the late 1990s had one massive computer that ran eBay. It was called a Sun Ultra Spark Ultra Enterprise 10,000. And there was a period of time where they were upgrading that machine, and eBay went down for a couple of days because something went wrong with the upgrade. And so then eBay's stock value, I think, would cut down by a third, like multiple billions of dollars, right? So somebody probably lost their job over why the upgrade didn't work at that point. But the model in the late 1990s was pour a lot of money into, have one basket, one really shiny egg, and protect it really well, right? The model that Google people were trying to do was, if stuff breaks, who cares? We're going to just deal with that failure and move on with that. And that meant that then they were also dealing with lower cost componentry, so gigabit Ethernet or 100 base T Ethernet, instead of faster networking like the supercomputers had at the time. So today, these are very profitable companies, and they're shifting what they're building their platform on, right? And that affects some of the design decisions for the software that they have for that. So you can see if you look in the high-performance computing and the scientific computing world, almost all computing applications are now written using something called MPI, Message Passing Interface. So like even if you're running on a shared memory machine, everybody writes their code on MPI because MPI will work everywhere. And then if the company that is building this machine goes out of business, well, I can use that machine. And so there's sort of become this sort of model about how you develop software. And that model is still being sussed out here because now there's enough money to throw in some more higher speed hardware. So for example, the Janus cluster that's here at CU, which has 9,000 cores or something like this, it actually has a different interconnection technology. It's not Ethernet. It's called InfiniBand, and it's like 40 gigabits per second in between nodes. So a much faster interconnect, and it has a different model of the way that it works than Ethernet does. That is increasingly being used in data centers. But the design decisions of Hadoop and these other things were done in the time for that. And that's why then some of it's changing now, is because of these different computing models. But it's useful to at least understand why it was done the way it was done. So there's this sort phase. So basically for any key, you're going to have a single reducer would have key 1 and then all of the values associated with key 1 for that. Even if different mappers produce key 1 values, they will go all to that same reducer. And a byproduct of this is that if the reducer dies, I think that the keys are stored in Hadoop so in other words, it's not until the reduction phase is done that you're going to get rid of the keys on the other node for that. And then you could do a secondary sort, and that was basically the sorting of the keys within a given reducer, if that was valuable. So like once they've all gotten to one place, then I can do a secondary sort. I've never seen an application that uses it, but I don't really do a lot with it.
So the mapping node gets some signal back from the reducing node saying, I'm done. You can
Yeah, there is an overarching scheduler that is, we'll look at some parts of what's there, but it's basically, what the overarching scheduler is doing is chopping the work up into little pieces, telling the map nodes, do this, do that, do these different parts. There'll be then a phase where it goes to the reduction nodes, but if, for example, one of the map nodes blows up and dies, then the scheduler is going to go and find another node and say, do that work that I told this one to do. Does it make sense? And so likewise, if a reducer blows up and dies, I have to have somebody else take over the reducing task at that point.
You have to go back and resend the map data.
I don't know whether it recomputes it or whether it resends it. I assume it resends it based upon what I've read on their implementation for that. But the glorious thing about this is you don't have to worry, right? I mean, you can walk up to have a map-reduced cluster, a Hadoop cluster, and just shut things off, and up to a certain extent, it should continue to function. For that. And again, we'll go through later on, and why would you possibly do that? And it has a lot to do with the failure probabilities in these systems. If you're dealing with jobs that have 10,000, 20,000 nodes, something's going to break on a regular basis. Or the hardware doesn't break, but the operating system has a problem, or something else goes on for that. So this is then the word count reducer. So this is so it's extending the reducer class, and so it's taking a text, an int, as its keys, and that's the input to this, and it's producing a text, the words, with another integer value. So all this is doing is, for every, so it basically has here the key, and then a list of ints. It's just adding them all up. So now if what I have is hello 1, so if I had these two sets of inputs here, what I'm going to get as the output of this is, for example, hello 2. Because what this mapper would have gotten here is hello and a list of 1 and 1. And then it would have gotten as input world 1 and 1, and by and a list containing 1. So the reducer here, all it's doing is adding up these words, or the count of words. The hellos may have come from different mapper nodes. They're at the same reducer node, and now it just adds them up. Okay? Now, there's an obvious stupid thing that happens here, which is that if I have, let's say, like in this file where it's hello, let's say, that's going to annoy me. Hang on. Hello world by world, the simple mapper would be emitting world 1, world 1. And I ought to be able to do that reduction stage before I do the shuffling. And so Hadoop actually has a mechanism to do that. In this case, this reduction, you'll actually use exactly the same code, but it goes into something called a combiner or combining phase. The combiner has basically the same type signature as the reducer, and it would usually be the reducer. And what that's doing then is the mapper is going to do its processing, and before it ships it across the network, it's going to do a reduction on that node. So, for example, it would have found if this whole sentence is being processed on one mapper node, instead of it producing hello 1, world 1, by 1, world 1, it would produce hello 1, world 2, and by 1. It just reduces the amount of data that's distributed across the network. And for an associative commutative operation like this, it should work just fine. And all it's doing is it's reducing the amount of data. It wasn't the CPU time. That's not the big issue. It's the data, because they had a fairly slow network connecting these things together. Does that make sense? So you can use these combiners, but it's not automatically done. You have to explicitly state that for that. So prior to the reduce phase, so this shuffle phase, we'll see that basically there's the shuffle operation for k hosts in your reduction set, for number of hosts in your reducer set. The way that the shuffle is working is you're going to take each of the keys of value, you're going to run them through some hash function, MD5, whatever, SHA-1, any hash function, it doesn't really matter. The goal is to just be able to distribute it evenly and uniquely across the reducers, and then that specifies where the host for that specific key value is. Right, so that's what the partitioning phase is. And that's not violated if you've done the reduction ahead of time at that point. So if you reduce it ahead of time, it'll be just fine. And so the combining can be done prior to this reduction phase. That. So you can specify, so we'll go through a little bit in the sample. This is all the job setup. So the previous two examples are the map and the reduce code. And those are two different classes. It's all enclosed in one class file. And then in the main routine for the job, you create a job data type and a configuration, and you basically are setting up information about how this job should run. So for example, here we're setting where's the code coming from. So in this case, it's coming from the WordCount class. Setting the mapper class, the combiner class. So this setting combiner class, if you don't do that, it's not going to automatically run a combiner for that. And so then you can set the reducer class. Those are just the two classes from above. You're setting output, what the output types are, some input path names and output path names and things along these lines. We'll see how these get used. And then this is sort of like the standard at the end. What this is then basically saying, job wait for completion, is fire it up, finish it, and then exit when you're done for that. Later on, we'll see that if you're trying to do a map and reduce phase followed by another one, your job section gets correspondingly longer because you're having to specify that graph of how the maps and the reductions are happening, right?
So you mentioned that you want to have the intermediate key value pairs kind of spread out evenly among your reduced nodes.
Mm-hmm.
How do you get that? In terms of how do you know?
You pick a good hash function.
Okay, even if you don't know what your data is going to look like, though. So you start.
That's right. So. No, it's not necessarily dynamic, but you can adjust the number of reducers and you can adjust the hash function. So realistically, what you're going to do there is so most of these. I was hoping to get a couple people to come in and talk about some things where they use Hadoop in sort of non-obvious examples. So I was talking to somebody out of Cable Labs actually about a month ago, and they used to work at Cricket, the cell phone company. And so they actually collect information, about 1 terabyte of data per day, from cell tower sites and from handsets about call quality and location and other things along those lines. And then they process that data to try and determine where to improve, where to put more towers or signal, improve signal quality or things along these lines. So they're dealing with, ideally, thousands of customers, right, or even millions of customers, and thousands of cell sites. So if what they're doing in their task, right, I mean, so they're probably doing things like, if they have a job record, which is from a call and a completion indicator, so they have some software on the phone that reports call quality back to Cricket Central. They probably have records, per phone number, maybe tens of records about, location where it is, and they're probably going to then try and sort it to what cell tower was I associated with, or what lat lawn was I at, or something along these lines to then be able to update statistics. So they're typically dealing with, tens or hundreds of thousands of pieces of data, right, or of keys, right? And so if you're dealing with a small number of keys, like if you have 100 keys or something like that, this probably isn't going to work that well, is the thing. Does that make sense? So other cases, so like if you're doing a MapReduce implementation of a Netflix recommendation engine, right? So there'll be one key set, which would be the instances of recommendations. I rated this movie this much, right? And then the users. So again, these are pretty large data sets for that. And there will be some natural size, and maybe it doesn't scale to 100,000. But the intent would be that if you started off small, you could scale to 100,000 without having to change anything for that. Which that makes it a little bit more inefficient for each one. So the result of the combiner is so these would be the outputs of the combiner. So instead of having the reducers where it would have these the reducer would not see these as the two sets of inputs. The things that would be coming out of the nodes would have been combined in this like this, where now world is 2 and Hadoop is 2 in that case. And it just reduces the number of records and the amount of data in this particular case. And by and large, you really should always do this combined step for associative and commutative operators, but not everything is. So there's a bunch of standard reducers that Hadoop provides. So there's an identity one, there's a log sum reducer, there's a couple of others. The reducer tends to be the more specialized code in a lot of cases than the mapper, it seems, for that. So then there's partitioning. And so partitioning is this phase where you're selecting what output host node a given key value should go to. And so there's a default partitioner, which is this hash partitioner, and it just does this. So it takes the key value, and in the Java world, there is, for any object, there's a way to compute a hash value for a given object, and so it just computes that and does mod the number of hosts. And it's not really the number of hosts, because I might have a cluster where I have, 1,000 nodes, and I've decided to allocate 256 of them for reducers, and at any one time, 256 would be used for that, but it's not like node number 237, it's my reducer number 237, which might be one node or another node from run to run. So you're not tying it to the physical architecture which you're running. So an example of where partitioning might be important is, let's say if your data set, the key value is a flight segment for an airline, and then the value would be the person involved. So in this case, Alice flew from SFO to LAX, Bob flew from SFO to Denver. I might want to be able to determine all flights from SFO and have, so in other words, that I want all of this. These are two unique different keys, but I might want all of them to be on the same reducer for some reason, so that one reducer is processing everything that comes out of SFO, if it makes sense. So in this case, what I would do is write code that would tear apart this tuple and return the hash of the first segment of the flight, right? And again, there you would be trying to, it's because you're planning on doing something where you want all the same SFOs on the same, all the same originating flight destinations on the same node. For that, and depends upon what your work is. So the partitioner is, so this is an example of an edge partitioner where it's a graph of particular things. So a partitioner here would be, given a key, just get a departure node and compute the hash code over the number of partitions for it. It's fairly simple code to be able to do that. Again, it depends on what one is trying to be able to do. So there's, Hadoop has a serialization mechanism. So that is a mechanism by which to send data from one node to another node, and to then have that data transferred in a reasonable type. So if you're sending, key value pairs or some tuple across, you have to pack that up in some format so that at the other end you can unpack it, and you know what the key and what the value part is for that. And so the writable class is the basis of that for Hadoop. We'll see this whole notion of serialization of data between different nodes come up in multiple contexts. This one is particularly noxious. Google uses something called protocol buffers. Oh, hang on. Did it lose it? It's not. There we go. So Google uses something called protocol buffers to squirt data from one node to another node. And it's a little bit more elaborate than what we're using here. We'll encounter this later on. So like in protocol buffers, you have a description about a message that's being sent, and it will take care of packing up the data and sending it across and compressing it and uncompressing it at the other end. And it allows different representation or versions of the data, like if you're adding on to things or having optional data, so on and so forth. In the Hadoop stuff, it's much simpler than what this is doing for that. So please don't barf again. Okay. It didn't work. So, but most of these are things, for example, like, writing Boolean values, byte values, text values, things along these lines. So these writables are ways of just encapsulating the concept of writing out data and then being able to accommodate the different types. And again, this is just sort of like why Java is awful. Is because you have to write a lot of different classes to basically just wrap things up into different forms. So, for example, you might want to define your own writable. If you were writing an edge, which would be a source destination node of an airplane flight, you might have to then write out something where there's a write data type where it's going to write out the departure node, and then you would have a corresponding read thing to be able to read these things in. So you're basically you're unpacking that class or the struct that you have and sending out the appropriate things that you need in whatever format, so that then it can be sucked in at the other side for that. So it's pretty much a standard thing that you have to do in almost all multi-node systems for that. So input is divided into files. Files are divided into splits, and then splits are processed not, it says by individual hosts, it should be mappers. An instance of a mapper you might have many instances of a mapper that runs on the same host over time. There are many different file systems, so the Hadoop setup that we have you can have local file systems, so that would be like what's on your virtual machine, and that's not really useful. Like, that's useful for trying something out. So then, it could use, files from ~Grunwald/sample input, for example. But it's not useful in a distributed context because my laptop isn't distributed across those different nodes. HDFS is the Hadoop file system that we'll get to in just a moment in a little bit more detail. S3 and Swift we're going to treat as basically being the same thing. S3 is the scalable storage system from Amazon, and Swift is an implementation of more or less the same concept implemented for OpenStack. And what these are is mechanisms by which you can, it's like a put-get file system interface. So what that means is, like, Amazon has a mechanism by which I can authenticate to Amazon, and then I can stick a piece of data in a file that would be named, like, s3.aws.com/Dirk Grunwald/some name, right? And that name might have multiple slashes in it, but we'll see that those slashes don't mean anything. It's just a flat namespace where it's just that tag. And then I can squirt, a couple megabytes of data into that name, and then I can retrieve it later on. And the retrieval, there's a permission and access control mechanism for that. I cannot seek to the middle of that piece of storage and get byte number 47. I can get the whole thing, and I can put the whole thing, period. That's all that one can do. All right? So that kind of a file system is useful for, let's say if what I'm doing is crawling the web, I might store each web page as an S3 file, with the key being the URL of the file. So the key would be the signature, the S3 signature, and then the value being the content of the web page. It's really designed for bigger files than that, but that is an example of what you can use. In Amazon's case, S3 is reliable, so the scalable storage system, scalable meaning that they can handle millions of files from hundreds of thousands of concurrent users at the same time. It's reliable in the sense that the file is then distributed across their storage system, and if one node goes down, you can still access it. So this is actually a fairly common storage mechanism for a lot of different applications, because it's so simple. I mean, you have to basically not want to deal with, I want byte 47. I can deal with give me the whole thing or not. For that. And then what you get out of it, like in S3's case, is you get Amazon scalability and their web footprint, their internet footprint for that. So as an example of this, I was mentally just going through, I don't think I can show it to you but there's a jobs at CU system by which people apply for jobs, and then they upload their CVs and their resumes and letters of reference and all that stuff. When I access that stuff, that comes from S3. So I go to the website, PeopleSoft or whoever it is that maintains this thing, they don't have to do anything in terms of having, availability of these people's resumes. So their front-end engine is a very simple thing that's basically just taken like person's name and link to a URL to Amazon. So their database and their database scheme is really simple, and all of the complexity of maintaining reliability and everything else is shoved off to Amazon in that particular case. And so, and there are a lot of data sets that are available from Amazon this way. So Amazon has, and we're going to be using some of these in some of our examples. So, for example, the 1,000 Genomes Project, the Google Book Ngrams. Here's the Common Crawl corpus. This is 541 terabytes of data, 5 billion web pages. This data set's freely available on Amazon S3 and released on the Common Crawl terms of use. So, if we were, that would have to translate into. Can I just browse it? I should be able to browse it, but well, I guess I can't browse it. Yeah, I have to figure out. I don't remember how to get from the S3 part to the, I think to the actual URL. For it. But you could just download it using wget or curl or something like this. You can download these different pages. And so if you then knew what the actual web pages were, the names that were the identifiers for them, you could just download them from that point. And that's kind of the benefit of it, is it's not the world's greatest file system, but it's obviously designed to store big honking amounts of data. And again, it's sort of a distributed key value pair for them. So Swift is more or less the same thing for the OpenStack environment. It's just another protocol for dealing with it, but it also has compatibility with the S3 system for that. There's a file system class, and the file system class, for example, handles the local and HDFS mechanisms for this. There is then this gets turned into a data input stream, and there's something called an input format. There's a whole host of classes here, and we'll go through exactly what it is. So let's assume that I have a big honking class. And in fact, what you really would probably do, like if I was crawling web pages, and if I was trying to then index and pull out information from the individual web pages, the way that Google would have done it, and I don't know about the common crawling database, is they would have files where it might be 2 lines of data, the first line of which would be what was the URL of this location, and the second line would be the content of that URL with all the spaces and new lines removed. So my file might have very, very long lines, but now one big file, and the files in the Google file system in S3 were designed to be, the order of 100 megabytes, something along these lines, not kilobyte or something like this. It's designed to be huge files. So a crawler would be going through a website and going to a particular URL, writing the URL out, sucking in the contents, take out all the blanks, take out all the new lines, write that out to the file, keep going on to that. It produces a massive file, 150 megabytes. That's now going to be the input to a mapper. The 150 megabytes, you don't want to chuck it to one mapper. That whole thing is going to be allocated into splits. So the splits might be like 10 megabyte pieces of this 150 megabyte file. The splits are going to then, so these vertical lines here are intended to represent the splits. They're going to be breaking this down into records. So the colors here are intended to represent the records. This is a fairly reduced version of it. So this whole thing is my big honking file. I have broken it into splits, and then the splits are going to be further subdivided into records. So in this case, if I have split this here, what I would do is I would look, for example, when I'm splitting this, I would look for the new line. That would be where the end of a record would be. So I'm going to be directed towards this big honking file, approximately byte 30 million. I'm going to snoop forward until I find my new line. And you're like, yep, that's the beginning of my split. Everything else is the previous person's split. Does that make sense? So I'm not sucking the data out or doing anything with it. I'm just going to noodle forward until I find a new line and go like, that's my end of line or my end of record indicator, right? And then approximately 60 million characters into it, somebody else is doing the same thing. And they're going to identify then what is the other part, the boundary, the split that belongs to me. When you're actually writing it, you don't have that view of the file as a whole. You're given a position, at least for text file representations, you're given a position, and then you more or less say, where is the beginning of that split? And then a bunch of code above that takes that information and then tells the mapper nodes where they're supposed to actually access this stuff. Does that make sense? So the data might be structured. In other words, it could be binary data, it could be text data. It could be whatever you want as input data for that. But for the original application, which was indexing crawls, it was text files, big text files. Does that make sense? This was a hard concept for people the last time we go through that. Like, it's just piles of text, but then you're using, some structure in the format of it. And obviously you have to somewhat agree to what that structure is. So there are a lot of different possible format types. So text input format, each line is a record. The key that's provided is the position in the file, right? So, and typically you're not going to use it for anything, but the value is the text. So if I just have a series of, like that's what WordCount would use. It just doesn't really care what the position is, but it wants the lines of the file, for example. You might have a KeyValue text input format. So that's where I have, for example, a key and then a tab and then text, the value at that point. We're going to use that when we do the patent database example, because that'll have like patent number and then some other information off in the split. A sequence file input format, so this is a specific compressed file format. So let's say if you've taken some other data and you've now turned it into a class that represents the key and a class that represents the value, and maybe it's more complex, right? So like maybe it's not just text data by this point. Maybe some of it's binary, maybe it's something else. So you can squirt it out as a record that then you have to write something to do the squirting out and the reading back in, the marshalling and unmarshalling of that data. But it can be this sequence file format where now you can seek to any of the different records in that. N-line input format, so that's just like the text format, but that would have been like if I had written the URL and then the contents as two separate lines as opposed to separated by a tab, I could use that, where it would be, oh no, I'm sorry. That's not. So no, that's where it's divided into n lines. I don't remember why that one is. Yeah, that one's using just the same text input format for that. So this is an example for like a lot of things that log files are processed for. Again, Hadoop is batch oriented. So like something that. So have people used Google AdWords before, seen what it does? So, or Google Analytics, sorry. So I can find access Google Analytics. So here's some Google Analytics for like the Moodle website. And if I go to this, all website data. So this shows, for example, activity over the course of the last month. Here's the beginning of the semester. Here's returning visitors, new visitors, access times. I can pull out information like behavior, site speed. So this is the access time for the average page load time in seconds, ranging from 2.5 seconds up to 5 seconds on different days for this. Right? So this is just all information from the CS Department Moodle site. And this is not, this is being done by having cookies in the Moodle site. And so that when a page load occurs, you're sending a little bit of information to Google Analytics about the time that it took to get all the information and everything else. The only thing that's done with that information is it goes into a log file somewhere. And so that log file contains data that kind of looks like this, like I accessed this page at this time. And maybe it says something else. But there's a time and then there's an axis over here of what was accessed. So now, if I could count all of the different pages with the given URL that were accessed, I could tell you what's the most popular page on a site. If I have the sequence by time by a specific user, I can give you the trajectory of that person through the website. Right? If I'm then following them from Moodle to whatever other website they go, I can figure out when they leave and go to the next place, at least the next one that I track by Google Analytics. Does that make sense? So all I'm doing in all those cases is I'm just collecting these little bits of detritus, and I'm writing them somewhere. And they're going to be probably have some unique identifier associated with me, so my cookie ID. And they're going to be on some big Google database thingamadooby. And every once in a while, they're going to go through and fire up the equivalent of a Hadoop MapReduce job. They're going to process this log, and they're going to digest all that data, and they're going to turn it into this kind of a report now that I can use. Does that make sense? So that's like a classic example of what MapReduce was for and Hadoop was for, is indexing and taking log data and things along these lines for that. And so that's all that, so that's an example of what one might do, is have something where the key is time and the value is the URL, right? And then if I want to count the number of unique visits to the URL, I'm just going to swap the key and the value. I'm going to have now the keys are going to be the URLs, because I want to then count the number of times that URL occurs in my path, for example. So there's a number of different things that you could conceivably do with that data. You can use it on back-end data that you're collecting, not even with cookies, like if you have an Apache log or something like that. So Moodle internally has a log that Apache keeps about web page access and all of that kind of stuff. Conceivably, I could analyze that data as opposed to the data that Google collects for that. So you can basically set what the input file format is, and you would have often your own input file format. You might have custom splits. So the custom split, so this is, for example, you're being given a job and a number of splits that this is supposed to produce. And you can then basically read these things. That's what the record reader and input format classes are. And there are a pile of them that are there in the examples for that. So the file input format provides the input format interface, and it decides where to split. You can override that if you want to. So for example, rather than having log file be a text file, the second part might be a subclass of something else rather than just text. So it might be like, instead of it being a URL, you know it's going to be a number, and so you turn it into a 32-bit int, something like that. Trying to remember this example. So this was, so this is then an example of turning things from a text thing to a writable, where a writable is, now I'm going to have a specific class of something. So for example, I might have a class which is a URL. So this is going to be not just a string, but maybe it's a URL class which has its internal representation as a string. But I now have accessor methods to get the base file name and the URI and all these different components. So this is just an example of how I take one type and I wrap it and make it be a writable, so that then the system can transport it between the mappers and reducers. There's an awful lot of code that winds up being basically just massaging types from one type of data to another in this. So in this particular case, this is just how you write the data out. So it's just writing it as a Unicode, as a string, reading it in as a string, conversions, and there are ways to then do comparisons as well for that. A record reader class allows you to then have, to do the specific, figure out where like in a big file, I'm sucking out individual records that I'm processing. The record reader is the thing that moves to the next thing. It's the class that implements that functionality. So they have lots of little classes to allow you to customize some of this work. And that's why when you look at when you look at this class hierarchy, your eyes kind of glaze over, because there's just a lot of it that's related to wrapping up something so that it's possible to substitute it with something else at that point. And in Java, all of that requires a new class for that. We'll see that when we go to like Scala, all of these classes, like this record reader class here, where it's just chopping things up into keys and values and stuff like this, you might be able to just do this like using a very simple in-place method using a lambda for that. And we'll see that when we get to doing this with Spark, that's sort of the model there. So the code becomes a lot less onerous in these other languages for that. So I'm going to skip this one here because I'll have some long examples, because what I was hoping to do was to actually have an example where what we're going to do is the first simple assignment that we're going to do is just basically getting hello world functioning so that you get your VMs and everything functioning. The second one, I was going to be having some web pages, and you're going to be basically pulling out the anchors, the links to other web pages for that. And so you're just going to be processing something that does URLs. I'll set some of these other, the readers and writers. You can probably do it with strings would be the more useful way to do it. For it, but we'll get back to it later on. And it's also, you can have things be a database if that's what you want. So your readers and writers don't have to be just generic vanilla ASCII text files for that. So they can be structured data from a database, if that's what you would like. So there's an output format. So it's like the input format, but you're not splitting anything up. You're basically just chunking out data. Each producer or reducer produces their own output. So we're going to see that if I have multiple reducers, I'm going to have files named like part blah for that. And then the actual output is the union of all of that data for that. But it's keeping the output into separate files so that the different reducers are not coupled to one another, that they can run independently for that. So common reducers text output format, so it writes key tab value. Sequence file uses a Hadoop binary format. So like if I've already processed a bunch of things in binary, I don't store it as ASCII numbers, store it as binary numbers. So this is obviously painful, right? I mean, like, I could not imagine having to sit and write this kind of code 24/7. It would kill me. But then I hate Hadoop, or I hate Java. So it just killed me from the first 5 minutes. So you're also going to be using lots of Hadoop jobs in sequence. I mean, obviously what you would wind up for any kind of workload that you're doing, you're going to have then a set of these classes that are going to represent these different data types, your most commonly used data types. And then you're figuring out how to combine them together and produce new reports and things along these lines. But this is like, good luck trying to get a B-school data analyst to do this. Like the person who's supposed to then look at all of that data from the Cricket Cellular and figure out like how they're supposed to do their analysis. This is not like Excel, right? This is not at the level of just a random person could do this. And that was basically a problem that Google had as well, was that they could write these big jobs to do like compute the Google Analytics, but sometimes they wanted to be able to do queries on data sets and get answers back pronto for that. And in certain cases, so Google had a system called Sawzall, which is very similar to Pig, which we're going to be using a little bit later. It lets you basically just do a query kind of like you would do an SQL query, and that would then boil it down to a series of MapReduce jobs. And in certain cases, what Google actually did was they would subset the data. So in other words, if they had, if you have 4 billion records of URLs and for a given website, and you're trying to determine, is this website overloaded? You don't need to examine all 4 billion. You could randomly select, 4 million. And that factor of 1,000 reductions means that maybe that could be done in a very quick computation and get an answer back for that. But they turned this into a query processing system that's more directly accessible by people. And so that's then where, like when you start looking at the big data landscape, there's all these tools, cascading and this and that. They're all ways to basically get around the fact that Java sucks. And that, you don't want to have to then formulate every basic query into this kind of a complex thing for that. So there's also something, so systems like Pig will generate the Java for you. Same will these other things as well. There's also something called the streaming API. So like if writing it in Java wasn't inefficient enough for you, you can actually have it be that every map operation invokes another process, which can then do the processing in any language you like. So for example, every map operation where there's key and value, it could invoke a Python program, which is then given the key and the value and does whatever it wants to at that point. And likewise, the reduction operator can also be done in a key and value. So streaming in this context basically means that you're getting these functions or you're getting these invocations one at a time to some other program. There's also in, do people know what SWIG? Anybody know what SWIG is? Oh, okay. So SWIG is if you have a library, like a C library, you'll notice that like if you look at languages like Python and PHP and even Java, you'll see that there's like the Open Computer Vision library. So it's a library of routines to do things in computer vision. And you see, by God, that's been imported into PHP, and by God, it's been imported into Python, and it's been imported into Java as well. Well, it's not like people recoded all that stuff into Python and PHP. What they did was they wrote interface functions that basically then let you take the calling model of PHP, and then it shuffles around the arguments and converts it from the data types and turns it into a native C call, which then calls the real OpenCV. And so you could imagine writing all that code to do that by hand. SWIG is a tool that automates that. So in other words, you give it the include files for your library, and it will then poop out a bunch of header files that you can then suck into, sorry, technical term. It will emit a bunch of header files that will then, you can suck into your Python library or your PHP library, and now you can incorporate your C code into that. There is a similar thing for Java, so for the MapReduce framework. Like if you've got a bunch of C code that does your key value processing, you can do that. If you want to as well. So, but it's more or less, it's logically it's the same thing as the streaming API for that. And then there's other interfaces to other systems that lets you then deal with more other packages that do statistical analysis or plotting of data for that. So in the last few minutes, let's go through HDFS. We're going to talk later on about other file systems, but HDFS we're going to see has we're going to wind up using it a fair amount. So it's this, the Hadoop distributed file system. And basically what it means is that we're going to have multiple nodes in our, these data nodes. And in the original implementation of it, you had these name nodes and data nodes. The name nodes stored where a file was, so by path name, and says, you know, like this file, user Chuck data 1 is on nodes 1, 2, and 3. And then you would go to those nodes to actually get the data for that. Hadoop, the first version of it was written like by one person at Yahoo Labs, and so this was good enough for what they wanted. The data is reliable in the sense that if node 1 goes down, the data may be replicated on multiple nodes. So this is actually, it's mapping to blocks, and then blocks are replicated across the nodes for that. But the name node was originally unreliable. So in other words, if the name node went down, you were screwed. For that. But they would then basically try and make this be as highly reliable as they could. So then a bunch of people started other companies to basically get around a poorly engineered distributed file system. So like Cassandra is a database that is a key value store. You have a key and a value. And it is also reliable, kind of like this here, but its name node is also reliable as well. And I'm certain that it's got more other features since then, but that's more or less what it was originally. So this HDFS was reworked for Hadoop version 2. So now there are multiple name nodes, and they maintain consistency between one another. And so now if you have one name node fail, it's not the end of the world at that point. It also brings what is called federated storage. This is basically as you have big clusters and marketing wants part of it and sales wants another, or engineering or whatever. For that. So the federated HDFS supports multiple namespaces, but a single common data space, and then what's it called? When you have a limit on how much quotas, things along those lines. And so there are these primary and secondary name nodes and other things. There's a bunch of commands. We're going to be using a few of these. So in the the system that we're using, we have to basically talk to the distributed file system through the Hadoop command because we don't have a native file system interface to it. But we can basically cat files to group files, do all the standard Unix things. Copy to and from, count the number of files, things along these lines. I'll point you to, when we get to doing this, to a web page that has more examples of this. There is also a way that you can mount this as a file system on your computer if you want to. So Fuse is something called, it's the user space file system, and it's another program that then would talk to Hadoop, and it makes it look like, I can do ls/hdfs, and I would see all the files there. I didn't set that up on the workstations, but it's not complicated to do. It's usually easier for people to deal with than having like lots and lots of HDFS commands for that. We're going to see later on that there are many other different file systems. So HDFS used to have these limitations. It was sort of reliable, but not really because of this limited name node, the mapping there. It's now actually much more reliable. A lot of places have a lot of data in HDFS because you have to bring it into HDFS. The other thing that's been done is you can now have many more adapters so that Hadoop doesn't necessarily have to talk to just HDFS. At the first versions of Hadoop, that's all it could talk to. So we'll see later on there's file system for this S3, Swift, Ceph, other things along those lines. So what we're going to do tomorrow or Thursday, is we're going to go through the Hello World program and setting up how to do that, and I'll have the assignment for the first, just please go off and do this and make it work. What we're going to see later on is we have the beginning setup of the cluster on our OpenStack system. You ought to be able to take this program and run it on that once it's been fully set up. And that'll have like 16 data nodes and 16 compute nodes and the whole 9 yards for that. And like without changing anything, you ought to be able to then run it on this much more scalable system for that. But we'll go through the mechanics of that on Thursday. And I'll put these slides up as well on the and put up the assignment, which is basically just check to make certain that your stuff hasn't broken yet for that. Okay, so we'll see you on Thursday.